Assalamu alaikum, myself Fariha Javed, and I'm here to present a topic named as silicon germanium alloys. First of all, if we talk about the introduction, so the foundation of group 4 element, group 4 semiconductors basically. So the history of the digital age is written in the atomic lattices of group 4 elements, while carbon forms the basis of organic life. Its heavier containers, silicon and germanium, from the substrate of modern computation. The evolution of semiconductor technology has been a relentless pursuit of manipulating the electronic properties of these materials to control the flow of information. So initially, the germanium was the material of choice for the first transistor due to its superior carrier transport properties and lower melting point. Here we get the point. What is the properties? What is the property of germanium? That was the superior carrier transport property, and the other one is lower melting point. And then this property made it as the early purification accessible. However, silicon eventually spurred germanium's dominance. It means that it suppressed the germanium's dominance primarily due to the thermodynamic stability of its native oxide, silicon dioxide, and its wider band gap, right? And this thing allows it to reliable operation at high temperature. Yet as the physical limits of scaling silicon based metal oxide semiconductor field effect transistors are approached, so the industry has returned to germanium not as a replacement but as a partner. Means they synthesize it as the silicon germanium alloys. And yes, it represents a term of band gap engineering, allowing for the precise tailoring of electronic property structure, lattice dimensions and transport characteristics. So this report provides an exhaustive analysis of the individual chemistry of silicon and germanium, the scientific logic behind their alloying, the thermodynamics and kinetics of their synthesis, and their widespread applications in microelectronics, photonics and quantum computing. If we talk about the individual chemistry and physics of silicon and germanium, so when we want to comprehend the behavior of silicon germanium alloy, one must to dissect the fundamental physiochemical properties of its constituent elements like silicon and germanium. These both resides in the group 14, means carbon group of the periodic table, sharing an isoelectronic valence shell, right? Means the configuration is same, like two electrons in the valence shell. So there is a differences in the atomic structure leads to the profound divergences in their macroscopic properties. Means it affects their macroscopic properties, not the micro one, but yes, the macro ones. If we talk about the electronic configuration and bonding, then we know that its atomic number is 14 and the electronic configuration is like this one. Means there are two electrons in the valence shell of silicon, while the germanium has the atomic number like 32, and it is configured as this one, and it also has the two electrons in the valence shell. So both elements possesses four valence electrons, facilitating sp3 hybridization, right? We get now about the hybridization as well. In this state, one s orbital mixes with three p orbitals to form four equivalent hybrid orbitals that are arranged in a tetrahedral geometry with bond angles of 109.5 degree. So this directional bonding drives both elements to crystallize in the diamond cubic structure characterized by two interpenetrating face-centered cubic sublattices displaced by 1 by 4, 1 by 4, 1 by 4 along the body diagonal. Then we know that the presence of the filled 3D shell in the germanium is a critical differentiator. It means the d electrons provide incomplete shielding of the nuclear charge for the outer valence electrons compared to the efficient shielding of the s and p core electrons in silicon. So this phenomena often referred to as the d block contraction or scanted contraction through more relevant for gallium, that results in germanium having a higher electronegativity than simple periodic trends might predict. Furthermore, the larger atomic radius of germanium, like it's approximate 1.22 Armstrong, and the silicon one was 1.11 Armstrong, leads to the longer bond length. That will be 2.45 Armstrong versus 2.35 Armstrong, and consequently the lower bond association energies. So the difference in bond strength manifests directly in their thermal properties, means that it might bring some change in their thermal properties also. So germanium has a melting point of approximately 938 Celsius, so significantly lower than silicon 1414, while the lower melting point of germanium facilitates lower temperature processing. It also makes the material more susceptible to thermal decomposition and dopant diffusion during subsequent high temperature manufacturing steps. If we talk about the crystallography and lattice constants, so the lattice constant A0 is a fundamental parameter in semiconductor, and also if we directly talk about the silicon and germanium, then the crystallography is the approximately 5.431 Armstrong, and while the germanium one was 5.658 Armstrong. So this mismatch between silicon and germanium is approximately 4.2%, means this is a difference. This is a latest mismatch. So what this mismatch done, this mismatch um, basically change the context of their crystal growth. When we deposit one material upon the other, means when we put a layer of one material on the other one, that 4.2% difference generate the immense elastic strain energy, right? If the deposited layer remains coherent, matching the substrates in plane lattice spacing, it is termed as pseudomorphic and is under significant stress, compressive for silicon germanium on silicon and tensile for silicon on relaxed silicon germanium. If the layer exceeds a certain critical thickness, then the strain energy is released through the formation of the misfit dislocations, which are generally detrimental to device performance. We have to determine it, and these things change the device performances basically. So electronic band strength, this is the main point. The utility of semiconductor is defined by its electronic band structure. We all know that how much we can use a semiconductor, where we have to use it, this all is determined, and this all is defined by the electronic band structure. The band gap, it matter many more than the other factors. The other factors also matters, but this one is the very very basic. So the energy landscape that electrons and holes traverse, both silicon and germanium are in direct band gap semiconductor, right? Meaning the maximum of the energy of the valence band at the gamma point k0 means k0, and the minimum energy of the conduction band occur at different crystal momenta, that is k vectors. So this necessitates phonon participation for optical transition. It means there this thing brings the need of phonon use, means we have to bring out the phonons, and that phonon participate in it for what, for optical transitions, making both materials inefficient light emitters compared to direct band gap materials like gallium arsenide. While we talk about the silicon, so the conduction band minimum is located near the X point of the Brillouin zone, specifically at 0.85 of the distance to the zone boundary. And if you talk about the band gap energy is 1.12 electron volt at 300 Kelvin. This is the main point. While we talk about the germanium, the conduction band while we talk about the germanium, the conduction band minimum is located at the L point, mean zone boundary in the angle 111 wrangle direction. That is the, we can understand it from the picture, basically comprising 4 equivalent valleys. So the band gap is significantly smaller, means it is 0.66 electron volt at 300 Kelvin. Okay, so notably germanium possesses a local conduction band minimum at the gamma point, that is only approximate 140 electron volt above the L valley minimum. Okay, what if we talk about the carrier transfer properties, then there is a silicon and germanium, that electron mobility and the hole mobility. So for silicon it is 1400 centimeter, and for germanium it is 3900 centimeter. And if we talk about the hole mobility, that is for 450 centimeter, for approximately 450 centimeter for silicon, and 1900 for germanium approximately. So the low hole mobility of silicon has historically been a bottleneck for complementary metal oxide semiconductor performance, where p channel um, oxide semiconductor mean PMOS, CMOS devices must be made physically larger than their N channel. So this counterparts to drive the same current. The integration of germanium via silicon germanium alloys provides a pathway to equalize these mobilities, as detailed in later sections on strain energy. Okay, there is a scientific logic of alloy. Why we make alloys of silicon germanium? So the synthesis of silicon germanium alloys is not a merely matter of mixing two elements. It is a strategic pursuit of band gap engineering and strain engineering. Right? The scientific logic of alloying. This is a very important question. But means why there is a need of making alloys of these two, like silicon and germanium? Why? Here is the answer. The synthesis of silicon germanium alloys is not merely a matter of mixing two elements. It is a strategic pursuit of band gap engineering and strain engineering. So the fundamental motivation is to decouple the electronic properties of the material from the fixed constraints of the silicon lattice, allowing for the degrees of freedom in device design that pure silicon cannot offer. This is the main reason. Okay, we talk about the thermodynamic solubility and miscibility. Yeah, you have to mix both of them. So the silicon and germanium are completely miscible in both liquid and solid states. Means these can completely miscible in both states, forming a continuous series of solid solutions described by the formula silicon 1 minus x. Oh, sorry, 1 ratio x and germanium ratio is x. Means 1 minus x is the ratio of silicon and germanium is x. When we mix, this is the ratio basically. X represents the atomic mole fraction of germanium, like here it is mentioned. This complete miscibility is attributed to their identical crystal structure and similar valency chemistry, while they form a solid solution. This is the point for the solid solution. The enthalpy of mixing is positive. Means it indicates a repulsive interaction between silicon and germanium atoms. So theoretical calculation using density density functional theory is used here. It suggests that silicon germanium alloys are thermodynamically unstable at 0 Kelvin and solid phase separate and should phase unstable at 0 Kelvin and should phase separate. Yeah, there is the separate in the phases, means they both are in the separate phases in the solid state. So, however, the elevated temperature mean when we change the temperature that is used for growth and processing, the entropic contribution to the energy, free energy, that is delta S, it dominates, and it also stabilizes the random alloy structure, and this allows for the fabrication of stable film across the entire composition range. Although care must be taken during annealing to prevent precipitation or clustering. So, what is Wegener's law and lattice energy? The lattice constant of the silicon germanium alloy follows Wegener's law to a first approximation. It means exhibiting a linear relationship with composition. More precise measurements reveal a small deviation modeled by a quadratic term, that is Boeing parameter. So here theta accounts for the specific elastic interactions in the alloy and the relationship in the scientific foundation of virtual substrate. By when we growing a thick graded layer of silicon germanium on a silicon wafer, means if we put down a silicon wafer and then we put a layer of silicon germanium on that, so one can create a virtual surface with the lattice constant that is larger than silicon. So any subsequent layer grown on the surface will experience strain determined by the difference between its natural lattice constant and that of the virtual substrate. So this allows engineers to mechanically stress silicon, that is tensile strain. We know very well about the concept of stress and strain. When we put a stress on anything, like when we pull a rubber band, right? We are putting stress on that one, and the position, the state it in that thing becomes is called strain. So this is a very simple definition of both. So when we put a stress on silicon or germanium, okay, the strain on silicon will be tensile and on germanium is compressive. We have to mind it at will. It will fundamentally altering their electronic band structures. It means when we put a pressure on these things, like on these both elements, not things, silicon and germanium, then what happens? Then their electronic band structure might changes. So band gap engineering. The band gap of relaxed silicon, that is 1 - 6 ratio germanium, germanium's ratio is x, that alloys varies continuously with composition x. However, this variation is not linear. Means for x it is 0. It is for x that is smaller than 0.85, that is silicon rich, and if the x is larger than 0.85, then it is germanium rich. This is the basic point. So in case of silicon rich, the band structure remains silicon like with the conduction band minimum in the delta values. The band gap decreases slowly as germanium is added. So when this is germanium rich, what will happen? A transition occurs where the L value means germanium like becomes the global minimum. The band gap decreases more rapidly in this regime. So the equation for the band gap of relaxed silicon germanium at 300 Kelvin is often approximated as, crucially in strained sorry, there is not equation mentioned, I'll share it. Crucially, in strained layers, the band gap reduction is significantly more pronounced. Strain breaks the cubic symmetry of the lattice, lifting the degeneracy of the valence and conduction band. For example, compressive strain in a silicon germanium layer on silicon splits the heavy hole HH and light hole LH bands. Means it pushes the LH band upward in energy and netting the band gap for more than a line alone would predict. So this dramatic reduction in band gap is utilized in heterojunction bipolar transistors, that is HBTs, to create large valence band offsets that block reverse hole injection, a key mechanism for high gain. Okay, so how we make the alloys, synthesis and growth kinetics. The fabrication of device quality silicon germanium requires epitaxial growth, the deposition of a crystalline layer that continues the crystal structure of the substrate. This is a non-trivial thermodynamic and kinetic challenge, primarily due to the disparate chemical reactivities of the silicon and germanium precursors and the stringent requirements for the interface purity. What are the growth techniques we use? We use the scientific logic, ultra high vacuum chemical vapor deposition. We also know very well about this technique. The second one is reduced pressure chemical vapor deposition, and the third one is molecular beam epitaxy, right? Okay, going back. So the fabrication of device equality silicon germanium requires epitaxial growth, means the deposition of a crystalline layer that contains the crystal structure of the sorry. Oh, we have to read from the growth techniques. Three primary techniques are employed. Okay, every technique offer a trade-off between control, throughput, and cost. Firstly, we talk about the ultra high vacuum chemical vapor deposition. What is the scientific logic for using this? Developed to overcome the issue of native oxide. We have talked about this now, silicon dioxide, and contamination at low temperatures by operating at pressure that is less than 10 raised to power minus 3 torr. The partial pressure of oxygen and water is kept below the threshold for oxide formation even at temperature that is low as 500 Celsius. So what is the mechanism? In this molecular flow regime, there is no hydrodynamic boundary layer. Reactant transport is ballistic. Growth is strictly controlled by surface reaction kinetics, that we can use hydrogen desorption, ensuring uniform coating of complex geometries, for example, vertical trench sidewalls. What is the advantage of using this technique? Excellent control over dopant profiles, and interface abruptness enables to growth of metastable strained layers that would relax at high temperatures. Second one, Reduced pressure chemical vapor deposition. What is the scientific logic? That operates at 10 to 100 torr. This regime bridges the gap between UHV and atomic pressure. UHV was the first technique that we had used. Mechanism. It typically utilizes carrier gas, hydrogen, and chlorinated precursors like dichlorosilane, and the presence of the chlorine suppresses gas phase nucleation, that is particle formation, and allows for selective growth on exposed silicon windows while preventing growth on oxides mask. What is the advantage? Higher growth rates than UHVCVD, making it the industry standard for high volume manufacturing. The third one is molecular beam epitaxy. Scientific logic. A physical vapor deposition (PVD), a process where elemental silicon and germanium are evaporated from solid sources using electron guns in an ultra high vacuum environment. That is 10 raised to the power minus 10 torr. What is the mechanism? Atoms travel ballistically to the substrate. Since there are no chemical precursors like hydrogen to resorb, growth can occur at very low temperatures. Advantages: ultimate control over layer thickness, means there will be a monolayer precision and doping. What is the limitation? Low throughput and high cost. Spitting from source materials can cause defects. What are the precursor chemistry and reaction kinetics? The CVD growth of typically utilizes hydride gases. Silicon sources like silane, disilane, and dichlorosilane. The germanium, germanium sources are germane. And the surface reaction kinetics. The growth mechanism is generally described by a Langmuir Hinsolwood model involving absorption and desorption steps. Adsorption. So the precursor molecules adsorb onto the surface sites, dangling bonds that will make dangling bonds. The decomposition and incorporation. The adsorbed species break down, incorporating silicon germanium into the lattice. So the hydrogen desorption, rate limiting step. This is the surface becomes passivated with hydrogen atoms. For growth to proceed, these hydrogen atoms must recombine and dissolve as hydrogen gas, H2 gas. What is the catalytic effect of germanium? There is a critical kinetic phenomena in silicon germanium epitaxy, is the catalytic effect of germanium on hydrogen desorption. So the germanium hydrogen bond energy is lower than that of the silicon hydrogen bond. So consequently, the presence of surface germanium atoms significantly lowers the activation energy for hydrogen desorption. What is the insight? While we add a small amount of germanium to the gas mix, drastically increases the overall growth rate of the film compared to pure silicon growth at the same temperature. So this allows for viable growth rates at the low temperatures that are required to maintain strain and prevent diffusion. What is the selective epitaxial growth? Silicon germanium and loading effects. In modern transistor fabrication, silicon germanium is often grown selectively only in the active regions, that is sources or drain, defined by oxide or nitride mask. This introduces the challenge of loading effects. So if we talk about the pattern dependency problem, the local growth rate and germanium composition depends on the pattern density of the mask. What if we talk about the macro loading, the variations in reactant consumption across the wafer led to gas depletion. It means it will deplete, it will load the gas. Microloading: on a masked wafer, reactants that land on the oxide mask do not stick. They diffuse or desorb and migrate to the nearest open silicon window, and the small window surrounded by large oxide fields receive a flux of extra reactants, and that leads to faster surrounded by the large oxide fields receive a flux of extra reactants, leading to faster growth and often higher germanium concentration compared to large open areas. I have repeated the line, sorry. Scientific solution: to combat loading effects, process engineers utilize chlorine based chemistry, means we use HCl gas here for reducing this phenomena. Etching: when we use the etching, HCl provides a competing H reaction. Here is the reaction: silicon plus 2 HCl, then it will give us the product silicon dichloride plus hydrogen gas. This etching is highly selective. It removes atoms from the oxide mask, means it prevents the nucleation, and it also removes the loosely bound atoms from the silicon surface. Okay, when we use the regulation by balancing growth of silicon H4 silane and etching HCl, the net growth rate can be controlled. So the presence of chlorine on the surface also modifies the different length of atoms and effectively flattening the micro-loading effect and ensuring uniform thickness independent of pattern density. What are the tailoring properties? Mechanism of control. The versatility of silicon germanium lies in the ability to tailor its properties by manipulating two independent variables. The one is composition and the second one is strain, and the strain is demonstrated by the epsilon. So tailoring band gap, the physics of strain. When we use this physics of strain, we can decrease the band gap of silicon by adding germanium, but strain allows for much more aggressive tuning mechanism. The strain breaks the cubic symmetry of the crystal potential. And what is the valence band splitting? In relaxed silicon germanium, the heavy hole HH and light hole LH bands are degenerate, means it have the same energy, means at the gamma point K0. So under compressive strain, means for example silicon germanium on silicon, this degeneracy is lifted. The HH band moves down in energy away from the gap, and the LH band moves up into the gap. Since the band gap is determined by the highest energy valence state, the upward shift of the LH band significantly shrinks the band gap. Conduction band splitting. Under tensile strain, for example silicon on relaxed silicon germanium, the six-fold degenerate or the delta values of the conduction band splits. So the two valleys perpendicular to the strain plane, means delta 2 lower in energy, while the 4 in plane valleys delta 4 rise. This lowers the conduction band's edge, reducing the band gap. Here is the insight. The strain induced band gap narrowing is often more potent than alloy induced narrowing. For instance, strained silicon is 0.8, for germanium 0.2 layer has a band gap closer to that of a relaxed silicon, means in the relaxed state of silicon that is the 0.6, and for germanium is 0.4 layer. So the bonus narrowing is exploited in HBTs to achieve the high gain with lower germanium concentrations, and it minimizing the defects risk. Tailoring the mobility, the physics of transport. So the effective mass reduction, when we split the conduction valleys, the tensile strain also populates. It means these values have the longitudinal mass, and these are perpendicular to the transport direction, and the transverse mass that is parallel to the transport direction. So electron moves into the channel, effectively feel the lighter transverse mass, increasing mobility. What are the holes here? Means the compressive strain. Compressive strain alters the curvature of the valence bands. The whole effective mass is highly anisotropic, and non-parabolic strain warps the wraps the band, such as the effective mass in the plane of transport is significantly reduced. When we talk about the scattering suppression, that is intervally scattering, in unstrained silicon, electrons frequently scatter between the 6 equivalent, means delta values, F-type and G-type scattering, assisted by photons. Strain splits the energy levels of these values. If the splitting energy is larger than the optical phonon energy, then the scattering between the lower delta 2 and upper delta 4 values is suppressed. Because electrons in the lower values do not have enough thermal energy to jump the upper ones. So what is the result? A dramatic increase in scattering time, further boosting the mobility. What is the limitations here? Tailoring properties via strain is bounded by the Matthews-Blaxley critical thickness. Okay. First of all, the thermodynamic limit for a given lattice mismatch, like determined by the germanium context, content X, there exists a maximum thickness below which the strain energy is accommodated elastically, that is pseudomorphic growth and the relaxation. Beyond HC, it becomes energetically favorable to form misfit dislocations at the interface to relieve the strain. And what are the consequences? These dislocations generate threading arms that propagate up through the active layer. Threading dislocations act as scattering centers and leakage paths, destroying device performance. What tailoring strategy we use? Engineering must design quantum wells and HBT bases that are thin enough to stay below HC. Alternatively, thick graded buffers are grown there where the germanium content is increased slowly. So this confines the misfit dislocation to the deep buffer layers, leaving a high quality relaxed silicon germanium surface at the top, that is virtual substrate, upon which strained layers can be grown. What are the application and methods of use? So the diverse application of silicon germanium have enabled us on the wide array of high performance applications, bridging the gap between digital computation and analog communication. Semiconductor application, first of all, the heterojunction bipolar transistor, silicon germanium HBT. So the silicon germanium HBT is the flagship application of the alloy. It revolutionized the radio frequency industry by providing performance comparable to gallium arsenide at a fraction of the cost. What is the scientific logic behind this? In a bipolar junction transistor, the current gain, it is limited by the injection of the holes. Means we inject the holes, and from this the base back into the emitter, means that return to the emitter. For stopping this, the base must be lightly doped, means we have to put an other element on that material, which unfortunately increase the base resistance and slows the device. So silicon germanium is basically a solution, and the band gap is smaller in this purpose and then that of the silicon emitter. So the valence band offset acts as a massive barrier to the whole bag injection. What is the result? Engineer can drop the base extremely heavily, lowering RB while maintaining the heavier gain, the high gain. Okay. Drift field engineering. Modern HBT is used as a graded base where germanium content increases from the emitter side, for example, 0% to the collector side, for example, 20%. Emitter side 0% and to the collector side 20%. So this creates a sloping conduction band, a quasi electric field that accelerates electrons across the base via drift, not just diffusion. What is the performance then? The silicon germanium HBTs have achieved cutoff frequencies FT exceeding 500 gigahertz and maximum oscillation frequencies. So what are the applications? 77 gigahertz automotive radar collision avoidance, sorry, not evidence, collision avoidance, 60 gigahertz optical fiber transceivers and low noise amplifiers for cellular handsets. So these are the applications. Next one, the strained silicon CMOS or BI BICMOS. Since the 90 nanometer technology node, silicon germanium has been integral to standard logic precursor CPUs. What are the method? In PMOS transistors, the silicon source and drain regions are etched away and refilled with epitaxial silicon germanium. What is the logic? The larger lattice constant of the silicon germanium source or drain exerts a uniaxial compressive stress on the silicon channel between them. And what is the benefits? The uniaxial strain boosts hole mobility by 50%, allowing PMOS device to match the performance of NMOS devices, which was previously impossible due to the intrinsically high mass of holes in silicon. Photonics. Silicon is transparent to infrared light, 1.3 to 1.55 millimeter, used in fiber optics, meaning it cannot detect it. Germanium, with its 0.66 electron volt band gap, absorbs these wavelengths efficiently. So the detectors, epitaxial germanium on silicon photo detectors, are integrated into silicon photonic circuits to convert optical data into electrical signals. So what is the mid-infrared? Silicon germanium and germanium cyanide alloys are being explored for sensing in the fingerprint region of the mid infrared, useful for detecting greenhouse gases and biological molecules. How used in the quantum computing? The platform is silicon to silicon germanium heterostructures are a leading candidate for spin based quantum computing. What is the logic? Electrons are confined in a strained silicon quantum well sandwiched between the relaxed silicon germanium barriers. What is the advantage? Spin coherence. Isotopically purified silicon has zero nuclear spin, eliminating magnetic noise, hyperfine interaction that causes qubit decoherence. So what is the scalability? Fabricated using industry standard lithography. What are the challenges? Valley splitting. The confinement of electrons in silicons or delta valleys leads to too low lying valley state. If the energy is splitting between these states in smaller variable due to interference disorder, it interferes with qubit operation. So engineering the silicon germanium interface to maximize and stabilize valley splitting is a key area of current research. So what are the applications of the non-semiconductor? Means non-semiconductor applications of silicon germanium is the while the user asks for uses except semiconductors, the physics of silicon germanium makes it useful in the areas distinct from the transistor logic. We can use it in thermoelectrics. It is a legendary material in the fields of thermoelectrics, the conversion of heat directly into the electricity. Scientific logic, and an ideal thermoelectric material must conduct electricity well, mean high power factor, but conduct the heat poorly to maintain the temperature gradient. Phonons. Phonons glass electron crystal, allowing silicon and germanium reduces thermal conductivity drastically due to alloy scattering. The mass difference between silicon and germanium atoms disrupts the propagation of lattice vibrations phonons. However, the electronic structure remains crystalline, allowing for good electrical conductivity. What are the applications? Radioisotope thermoelectric generators, RTGs. We can use them in the RTGs. Why? They are uniquely capable of operating at very high temperatures for decades without degradation. A regime where with the other thermoelectric materials like bismuth, telluride fail. Micro electro mechanical systems material, polycrystalline silicon germanium. Scientific logic is standard silicon requires the deposition temperature, and this is too hot for wafers that already have aluminum or copper wiring, right? So polysilicon germanium can be deposited at much lower temperatures. So application, this allows for MEMS last integration. Accelerometers and gyroscopes can be built directly on top of finished CMOS readout circuits, creating compact monolithic smart sensors for automotive and consumer electronics. So this is the table. Basically, if you directly go onto this table, this is a table for the key advantage, the material, the band gap, and why we use it. This is the basically summary, right? The strategic evaluation is silicon germanium an excellent material? Yes, it is an exceptionally versatile and high performance material, and its excellence is defined not just by its raw physical number but by its strategic position as a bridge between the commodity world of silicon and high performance world of compound semiconductors. And here the properties: the process integration, band gap flexibility, whole mobility recovery, high temperature resilience, and the challenges and the limitations are the defects, the thermal conductivity, the cost. And here is the conclusion. The chemistry of silicon and germanium, governed by their positions in group 4 elements, it creates a unique opportunity in material science. Like individually, silicon offers the stability and scale required for the information age, while the germanium offers the agility and speed required for the communication age. So by combining them into the silicon germanium alloys, scientists and engineers have unlocked a material system that transcends the limitations of its parts. Through the rigorous application of thermodynamic epitaxy, quantum mechanics like band structure and mechanics engineering, and also also depleting the defect. Silicon germanium allows us to manipulate the fundamental behavior of electrons and holes. It enables a high frequency radar that guides our cars, the optical links and that connects our data centers, the logic gates that power our processors, and the thermoelectrical generators that power our exploration of the outer solar system. Silicon germanium is not merely a mixture; it is a physical embodiment of the or mastery or the solid state. This is all for now. Thank you so much.